Hello again. We can now
Hi.
continue with the demo session on machine learning operations, which will be presented by Stefan Andonov. So Stefan Andonov is a researcher in the field of machine learning and data engineering with several years of experience. He is currently working as a teaching and research assistant at the Faculty of Computer Science and Engineering, Cyril and Methodius University in Skopje. Additionally, he is a data engineering lead at Loka, where he designs and implements data engineering and machine learning architectures for life science and healthcare companies in the USA. Stefan, I will leave the screen to you now.
Thank you. Thank you. Hi, everyone. Nice to see you and meet you all. Unfortunately, I don't have like a extended monitor over here, so let me see how the sharing. I want to minimize this part somehow. Is it possible? I guess it is. Okay, perfect. And this as well. Okay, so just few slides in the beginning. And let me turn on a timer so I don't go above time. Um, just some slides on what will be presented in the demo. It's related to the talk that Professor Majarov gave before me. So we are going to see two tools. One of them is MLflow, which can help us to track experiments, track the runs of the experiments, also register models that we see based on the previous experimentations have been best in certain metrics. And the second tool that I'm going to showcase will be DVC or data version control. So MLflow, as I said, we will run two experiments. I'll give some detail about what is the use case that we are going to work on in the demo, what are the differences between the experiments that we are going to run. And after running an experiment, we will find the best model in the experiments based on the several runs in that experiment, and we will register that model in the model registry of MLflow. But also, if we find a better model after running a new experiment in terms of some classification metric, in this case, we will update the version of that model. So we will get a second version of the model. Uh, DVC stands for data version control, but actually it's not data version control. It supports data version control. So DVC is a tool that integrated with Git can help us to create version control for the datasets that we work with. But DVC itself, it's not providing that version control. DVC is extremely helpful if we are working with larger datasets because if our machine learning project is connected to a Git and GitHub remote repository, when we push our commits to that GitHub repository, we are not required, when we use DVC, we are not required to push the large dataset on GitHub. We can just push some .dvc temporary helpful file that will just say us where we can find the original version of the large dataset. And DVC, as I said, uses a different remote storage. For example, if our code repository is hosted on GitHub or GitLab or Bitbucket, we can use an entirely different remote storage for our repository, like Google Drive, S3 on cloud, etc., etc. So for the setup of this demo, I will share the code on the GitHub repo that has been provided by the organizers. If you want to replicate my environment entirely, or you can use, of course, your own. I'm using integrated development environment PyCharm from JetBrains, but feel free to use also Visual Studio, anything of your choice. I'm using version 3.11 of Python, if I'm not mistaken, on my computer. I'm creating a virtual environment through PyCharm. So PyCharm offers a user interface where you can easily create a virtual environment. And I'm using Jupyter notebooks, which of course required first to have installed the Jupyter library using pip. The tools can be installed very, very easily locally if you want to use them like I'm going to use them today. They are simply two Python libraries that you can install using pip. So pip install MLflow and pip install DVC. And after you install them, there are differences on how to use them. MLflow, as a machine learning operation tool, offers a user interface which you can start very easily with using MLflow UI on the terminal, and this will create a web page, a dynamical web page user interface, which will be connected to all of your experiments and model that you perform locally. You can also install MLflow using Docker. You can run a Docker image and create a container. This, of course, enables you to use this tool in different capacities, not just locally, but also on some other machine, in a cluster, etc. The demo will be, I'm going to showcase the two tools parallelly. So whenever I do some modifications on the dataset, I will run certain DVC steps. And then I will run the experiment with MLflow. So it's not going to be separate sub demo for DVC and MLflow, but it's going to be integrated into one joint demo. The use case that I'm going to use over here is a classification dataset. So we will be running experiments to perform and find the best model for breast cancer classification. This is a publicly available dataset available on scikit-learn. Also, there is a paper related to the dataset. The dataset is a tabular dataset, and it consists of 30 numerical features, so continuous feature, which represents some kind of features extracted from the images that are related to the dataset, and it's a binary classification problem. So the class of 1 represents that cancer is detected in the image, and 0 represents that it's not detected. So it's a healthy patient. So the use case that we are going to perform are, I'm going to run now 2 experiments, but these 2 experiments with MLflow and track them with MLflow. But these 2 experiments can easily be 10 experiments. They can easily be daily experiments. So this can be, as Professor Majarov was explaining in the lecture, this can be a regular daily pipeline that will enable us to perform experiments on the current training dataset that we have. Evaluate that, and if we find a better model today, we will update that model in the model registry. So the first experiment, what are the differences between the 2 experiments that I will run? The first experiment will contain a very small portion of the training dataset, like 20-30%. And why am I doing this? This is to simulate that when I run the experiments for the first time, I will probably not find the best model for this problem, machine learning model. Also, I'm not going to use all classification algorithms that I have planned in this experiment. So I'll just use 2 out of 3 with combinations of different hyperparameters. In the terminology of MLOps, when I'm running different machine learning models with different hyperparameters, I'm performing an experiment. Each model and a combination of hyperparameters is called a run on the experiment. So here in this experiment number 1, I will have 2 classification algorithms with 2 hyperparameters combinations per each. So I'll have 4 runs in this experiment. In the second experiment, I will use the original training set, so the larger training set, which represents 80% of the full data set that's available on this link over here. But I'm also going to extend with another classification algorithm with combination of hyperparameters. So I'm going to have 6 runs in the second experiment. For each experiment, I will identify the best run out of the 4 or the 6 runs. And this run, I'm going to use this run and the model parameters for this run. I'm going to use it for the first experiment, I will register this model in the model registry. But for the second one, if the best run of the newest experiment is better than the previous best run of the first experiment, I will update that model in the model registry. And this can be a process, as I said, that can be ongoing daily, hourly, weekly, depending on your use case that you have. So this is all in terms of the data slides. I'm going to move now into the integrated development environment, where first we will start with exploring the data that we have. I'm going to zoom in. I think it's going to be fine this way. So this data set can be easily loaded up using the load breast cancer method from scikit-learn. And the data of the dataset looks like this. As I said, 30 numerical features. The dataset consists of 569 patient data, images, and these are the features extracted from those images. The target in the dataset is, as I said, binary class problem. So we have 0 or 1, where 1 indicates that cancer has been detected in that picture. So I'm going to split this dataset into training and testing. As I said, the test size is 20% and the training size will be 80%. This train test split method will keep the distribution of positive and negative classes in the training and in the test dataset. And we are going to get now 455 rows in the training dataset compared to the 569 from the original. So for the testing dataset, we will reserve 114 rows of data. What I will do now, but before I move into this, let me start also with DVC. So in terminal over here, I am going to, as I said, DVC is a util tool for Git. So we need to create this. This is not a Git repository at the moment. So I will initialize this as a Git local repository. It requires me to set the main branch name, okay? But also now I will initialize a DVC repository. So just DVC commands are pretty much same as Git command, just the prefix is different. So DVC init. Okay, now this is also a DVC repository besides being a Git repository. So here we have some hidden folder .dvc that has been created just in the same way as we do have, ls-al, just in the same way as we have a .git repository for the Git metadata over here. So what I'm going to do now is get back to the notebook. I'm going to create pandas data frames for the train and the test and the X and the Y data. And I will join all the train data. So I'm going to join the X train and Y train into a train data frame and X test and Y test into a test data frame. So I'm going to assemble the dataset. When you load it with this library, it's split into the X and Y, into the features and the target. But now I'm just going to join it all together. So now the training dataset with 455 rows looks like this. We have the 30 features and the last column for the label. What I'm going to do now, as I said, for my first experiment, I'm just going to use a very small portion of this training dataset, like 20%. So I'm going to create this data frame train df reduced, which will contain a sample of 20% of the data. So 91 rows out of the 455. Why am I doing this again? I'm doing this to simulate bad accuracy. It's not going to be that bad, but it's not going to be at the best possible accuracy for the model. So what I will do now, I will save the reduced data frame in the data folder in the CSV file train.csv and also the testing file. I'm going to save it in test.csv. So here they are. So let's see how will now this work with DVC. What will I do with DVC in this situation? So I will do now, just as you work with the Git files, you need to add them into staging first before making a commit using the add command. So I will say DVC add everything that's in the data folder. So data test.csv and data/train.csv. Okay, so now what has this produced? I don't know if you realized, we suddenly got two new files over here. The first file is, so for the both files, I got a file with the suffix .csv, DVS, sorry. And in the file, I'm having the following things. I'm having the hash value of the file calculated, the size of the file calculated, what hashing algorithm has been used, and the path to the file. So this produced metadata for the current version of the CSV dataset. Automatically, when doing the DVC add, you get a suggestion what you need to do in terms of Git, because this is, as I said, helping Git perform version control of the data. In Git ignore over here, the test CSV and the train CSV files have been added automatically. Why is this happening? Because as I said in the slides deck, DVC helps us with large files, regardless of the size, but it will help us not to push all the files on Git, because we don't want to, it's very tricky to work with large files. You need to enable LFS for that, to push them on Git. So this will allow us to keep maybe the dataset in another repository, but in the Git repository, we will just have this metadata for the files. I'm also going to do a commit now, git commit -m version 1 of the dataset, something like this. Okay, so let's now continue with the MLflow piece of work. We have created our first version of the dataset. As I said, the training dataset is very small now. It's not that huge. So installing MLflow, this has already been installed before, but if you need to install it, it's pip install MLflow. Also for the DVC, as I said, pip install DVC, which in my case, it has already been installed. We are going to start the MLflow UI in the same directory where we are at the moment, so EuroCC MLOps. Okay, this will open on our homepage on port 5000. It will open the UI. So this is how the MLflow UI looks. You have two tabs over here, one for the experiments, another for the models that you will deploy or save, register into the model registry. Currently, I have no experiments conducted, which is something that I will start doing now. Okay, I have this, I'm just going to minimize this terminal now. I have this like a counter of the number of executions that, so this is like a tracker number for the number of experiments performed so far. So let's go with the code first before I run it. Actually, I can run it because it takes some time, and I can explain the code while waiting for the run to be completed. Okay. Actually, one more second. I need to. I need to comment something in the first. So as I said in my first run, in my first experiment, I will not use all the models. Let's start step by step. So what is happening over here? First, we are loading the classification dataset that I prepared using the other notebook. This dataset is also saved on DVC. So we have a version of this dataset saved on DVC. I am creating the X and Y from the train and the test dataset. And then I'm saying that I will be starting MLflow experiment, which will be named breast cancer classification experiment number, in this case, 1. In the next step, we are defining all the models that we are going to use. So we have logistic regression and support vector classifier in this experiment. This element in the tuple is the class that we need to use for this model. So logistic regression from scikit-learn, linear model, and SVC, support vector classifier from scikit-learn SVM package. Here we have a list of all the model parameters that we want to explore for that model. So I want to, when I'm testing logistic regression, I want to test with different C value and different number of max iteration. And for support vector classification, I want to test different kernels with a different property for the C value. This can be easily extended, so dynamically, with multiple hyperparameters that you want to try out. Also, this doesn't need to be hard-coded in the code. This can be some YAML file, which you can load up dynamically and therefore run all the models and their parameters that you like. So for this first experiment, as I said, we are starting to iterate this dictionary. So we're iterating the model class and the parameters list. Then we're iterating all the parameters in the parameters list. For each of the parameters and the models, we are starting a run within the experiment, breast cancer classification experiment number 1. We give some name to the run, like the model name and the index number of the parameters list. We create the model with the scikit-learn class. We call the fit on the training dataset. We predict the testing dataset, and then we calculate relevant classification metrics for this dataset, like accuracy, precision, recall, and F1. F1 is like the best parameter, which also incorporates precision and recall. So accuracy, it's not always the best parameter, depending on how balanced the dataset is. And now when we are during the run, when the classification and the testing and the evaluation is done, we need to lock all of these things into MLflow. We lock the model name. We lock all the parameters that we have used for this model. So like for SVC, we lock the value of C, we lock the kernel type. For logistic regression, we lock the max iterations and the C parameter again. We also lock all the metrics that we have computed, and then we lock the model itself. So the model that has been fit, we log it, and in this way, all the binary data for that model will be saved locally, and we can also access it on the UI. And we print some logging over here. So let's see what happened now locally. Locally, we have already a new folder named ML runs. We need to, this has not been saved. Okay, I probably need to run it again. I deleted the previous run because I had a mistake. This now has created for us a new folder in the ML runs, which has 4 runs, as we said before. And for each run, we have we have some metadata, which says, this is the artifact, this is the run name. Also, we have for the whole experiment, we have some data. Here it is, like the name of the experiment. The runs are part over here. We have the metrics computed, like here is it, F1, precision, recall, the parameters that were chosen, C, max model, max iteration, the model name, some tags if they're present, and the artifacts. So this is very important because when we select a model, we will save its artifact, and later when we deploy that model, we can use these artifacts to load the model and start model serving in production. Okay, but I wanted to show you how it looks in the folder, but the good thing is that you can also see this in the UI. So you can see the list of all the experiments in the UI. You can also perform some comparison of the results. So I'm going to do that also programmatically, but you can do it on the UI as well. So let's say I want to compare all the runs of this experiment. I want to give them on some scatter plot visualization. I want to visualize based on the model name and I want to show the F1 score. So we can see now on this scatter plot that the best F1 score for this experiment is provided by the logistic regression model with F1 score of 0.966, with max iteration of 200 and C of 0.5. So this is the best run for this experiment. So next, I'm going to proceed in the demo. Let me get back to the code over here. I'm going to proceed with, of course, this. You're not going to do this manually all the time. This is just a nice UI for you to take a look what happened. I'm going to do this programmatically. So select the best model and save it. So the model name that we are going to be saving will be breast cancer classifier. Sorry, I need to comment this. This is not necessary. Breast cancer classifier best model. So I'm going to get the experiment number 1 in this case, and I'm going to find the best run from that experiment using the search runs method. Okay, now the best run, when I'm searching for the best run, I'm telling sort the runs by F1 score in descending order. So if they're in descending order, the first element will be the best run. Here it is, max results 1. That's why I'm saying I just want the best result. So here it is, the experiment ID, the run ID also, that's this run. We can also see it locally over here with F1 metric of, sorry, scrolling is a bit hard. F1 metric, as I said, of 0.965517 from model logistic regression is the best model for this experiment. So what we are going to do now, we are going to register this model. Let me just go through the code over here. But what we are interested in this case, because this model is not registered yet. So there is no registered model. This is the first time we are registering a model. So what will happen in this case, in this try-catch block, I'm going to just minimize it for a second over here. When we try to get the model named breast cancer classification best model, there's going to be an exception here because the model is not registered yet. So we will go in this exception handling code over here, which will register the model for the first time. So the best run, based on the run ID that we have identified, AF, A4F, etc., is going to be registered in the model registry of MLflow. Let's run this. So yeah, model registered for the first time under the name breast classification. And let's take a look on the UI. So let's not just take a look on the code. In the UI, we have the model. Version 1 has been created. If we open the version, we will see the source run. Here it is. The source run is from this model logistic regression parameters combination 1. And we can navigate on the UI to that model. So this is the current best model, which has been registered, and we can use it. Here are some ways how we can use this saved model on this spot, how we can save it in order to do predictions in real time. So this gives us like a manual, also how you can do it on Spark if you want to use a data engineering, a data processing framework. This gives us a code snippet on how we can integrate this in order to serve the best model possible. Here are all the artifacts, the data. This is like a YAML file, but also we have the pickle file for the model, requirements needed to install to use this model, etc., so that we can very easily, as we said, with here are the metrics of this model that have been saved, how very easily we can integrate this model in our code in the future. Okay, next I'm going to increase the number of executions because I'm going to perform a second experiment on this dataset. What will happen in this situation? Now I'm going to use the full training dataset. We have a raise hand. Maybe because I don't think we can unmute you. Maybe we can wait until the end for questions. That sounds better. Not sure what's the best situation here, or it was a mistake.
You cannot
Okay.
participants. If they have any questions, they can write it in the Q&A.
Okay, so I can answer them at the end. So better. Okay, thank you. Okay, so let me just verify that I run this. Yeah. Now we are going to perform a second experiment. As I said, in this second experiment, now I will save the full training data set in the train CSV. So imagine this, that we are simulating that during the course of time, we have gathered more and more historical data, and we are ready to train and test our model with nicer data. But let's do also the DVC part of work over here. I'm going to need to open a new terminal now. So now what we will do is basically, again, we need to add this new version into the DVC stage. So I will say DVC add data/train.csv. I'm going to do the same for test, even though there are no new changes in the test dataset. Okay, the file has been added, and we will add the .dvc metadata files into Git. Okay, if we open those files, especially the train CVC, we will see that now the size has increased a lot of this file, and also the hash code, hash function value for this file has changed. I'm also going to do a commit, git commit -m, version 2 of the data prepared, something like this. Okay, we have one file changed, which is basically just this file. And these two things have been changed. That's why we have 2 insertions, 2 deletions. Okay, now that this has changed, we have a second version of the dataset. I am going to get back to the MLflow demo now, and I'm going to run a second experiment. But in this second experiment, I will also use another model, which I think it will provide better results in terms of F1 score. Yeah, that's pretty much it. Nothing else to change over here. So this is really this is the whole point. Like even I didn't even have to uncomment this code. I could have just changed some YAML file and then just run the script to do the training and the finding of the best parameters and the tracking of the experiments. So this can be fully automated just with click a button on some UI and perform the script. Okay, now it's going to be breast cancer classification experiment number 2 as we increase the execution variable over here. But as I said, it's going to use a larger data set for the training, the same testing data set, and also 2 more runs related to random forest algorithm. Let's run this. It will take a few seconds, but if we refresh over here, we will see that now a new run has been added. But let's take a look on the, okay, probably it's still running. Yeah, it has 6 runs. Let's take a look on the UI. So we go back to experiments. Now we have the second experiment, which compared to the fourth one contains few more runs. Let's also compare the results again. So all runs, we compare them on a scatter plot based on the F1 score. We say, give me the model name. So we will see now that random forest achieves an even higher better score F1 of 0.97, which is better than the current version 1 best model which had a F1 score of 96.55. So what we are going to do now in the code, let me get back to the code. This is not running, okay. What we are going to do now is for the latest experiment number 2, I'm going to identify again the best run. And the best run is 653. This is it, with model random forest and F1 score of 9722. Here it is. What will happen now in the next piece of work, because now the model already exists. We have already registered this model and we have a version of it. What I'm going to do now, I'm going to create a client, MLflow client, and I'm going to get the latest version of this model name, of this model, the breast cancer classification best model. I'm going to get the max of the version. So like if we had multiple versions, 1, 2, 3, 4, 5, 5 would be the last version. So I need to get the number of the last version. And I'm going to get the F1 score of the latest version of the model. So I get the run based on the run ID, and I get the F1 score. And now I check if the latest experiment F1 score, best run F1 score, is better than the registered model best F1 score. In that case, I will register this model from the latest experiment under the same model name. And this will automatically create version 2 of that model. If not, we will just say the current model has a worse or equal F1 score to the current best model, so no need to update that version. Okay, because 0.97222 is better than the current best F1 score, the breast cancer classification best model in the model registry will be updated. So we have created a version 2 of this model. Let's take a look now on the UI. So on the UI, we have 2 versions of this model. Here is the version 2. Which is with the random forest algorithm, as we said, with the metrics of 0.9722 for the F1 score. And again, I want to emphasize, this can be a script that you can run daily every time that you have some change in the dataset. And how can you know that you have a change in the dataset? Well, that can happen with DVC and Git. That you can connect them in some way that you will know that there has been a change in the dataset. You can check the current hash code of the in the training dataset with the previously saved hash of the dataset, which is actually available in the latest Git commit. One more thing, so this is what I had in plan for the MLflow. I think I'm right on time, but one more thing for DVC. Let's say that we have some situation like Professor Majarov mentioned that, let's say, in the latest version of the dataset, you have included data which is personal, and with GDPR, you received requests that you need to delete the data. So you need to return to a previous version of the data. Let's see how can that happen actually. If we do git log, we will see that we have 2 commits. One commit for the version 2 and another commit for the version 1 of the dataset. In version 2, this is where, let's say, this is where the personal data was added, even though this dataset doesn't contain any personal data, but let's say this is the moment where this happened and you want to do a rollback on your dataset. So what you will do in this situation, you can say, you can do git checkout to the commit, to the version 1 of the dataset commit. And you can do this just for the train file. No, sorry, not the metadata file. Okay, so now this has been changed. This has been changed. I don't know if you realize the change on the UI right away, but it's now with a different MD5 cache and a different size. But this will not change you the train.csv file. It's still the large 455 rows dataset. If you want to also restore the data that you have locally to this version, in that case, you just need to perform DVC checkout. Okay, in this case, here it is, automatically, it changed. The data is it has 91 rows now instead of 400 and something rows. Okay, this is what I had planned for the demo. Thank you for your attention. And of course, I'll be happy to answer any questions that we have.
Thank you, Stefan, for the.
I hope I'm right on time or not late.
Yes, you are right on time. But
okay, how can I stop sharing now? It's a bit stop sharing. I usually here it is, stop sharing. Okay. So happy to share again if there is some question to that.
There are some questions.
Yep.
Why the F1 score is more important than accuracy metric?
Because this is a binary classification problem. Good question, definitely. It's like the F1 score, as I said, is like not average. I forgot the right name. A balanced average between the precision and the between the precision and the recall. Let's say that in this data set of 600 cancer patients, we only have 20 samples which are positive or they have cancer. And if out of those 600, we predict, so let's say 580 are healthy and just 20 are with cancer. And we predict all of the healthy patients, but we don't predict any of the patients with cancer. In that case, the accuracy will be high. It will be in the 90% something, right? But the correctness of predicting whether a patient has cancer is 0. F1 score makes a balance between those two metrics, the precision and the recall. That's why it's pretty much a standard important metric for classification problems. I hope I covered the answer.
Another question.
Yep.
How do we determine which type of regression type is most suitable for a model? Is it done through trial and error, or is there any other way to understand this?
Mm-hmm. Well, there are so here I just added two parameters, two setting of parameters. But yeah, it's trial. You need to do trial. Yeah, you need to do trial and runs and identify. And this is where ML Flow can help you to track your experiments. Also, there are a lot of, as Professor Majarov mentioned, there are also a lot of tools that can help you in hyperparameter optimization. So there are algorithms. We have worked together with Professor on a tool named Teapot, which you say, okay, I want to play around with logistic regression. Please find me all the best parameters for logistic regression. This tool is based on genetic algorithms from AI, and it will say, okay, I've worked with these parameters and these are the best parameters. So yeah, the answer, in the long story short, is experiments, a lot of experiments.
Another question. How is this different from doing cross-validation with scikit-learn's tools like grids? Does using DVC only make it easier to access and assess models, metadata, and save them?
Yeah, excellent question. I'll start with the second sub-question for the DVC. I didn't mention that, and thank you for reminding. So DVC can also use to, as we said, when we select the best model, we have some metadata for that model. We have the pickle file, for example, the YAML file. DVC can be used to keep track of those as well. like the scenario with the GDPR, we might not just need to get back to the previous version of the dataset, but we also need to get back to the previous version of the model. Using DVC, we can achieve that very easily. So for the first question, how is it different from cross-validation and grid search? It's a part of it. So doing cross-validation and grid search is one experiment, but you will do multiple experiments. You can do the experiments daily, monthly, weekly, hourly, depending on the use case. So consider cross-validation or train test split, and then grid search for parameter optimization. Consider them just as a tool in order to perform one experiment. But when working with production ML, you need to perform a lot of experiments because the data changes and you need to change the models. Therefore, I hope I covered everything.
So another question. Do we have to have Git DVC every time we update the model that we need to update as well?
Well, if we want to do tracking on the model metadata, I didn't in the demo, but if we want to keep track of that and maybe have version controls of the model data, yes, absolutely, we need to. So we need to do DVC add on the whole folder where the ML runs were stored. There was a folder, if you remember, in the demo, ML runs. No, sorry, is the name correct? Yeah, ML runs. So on that whole folder, we need to say DVC add ML runs. And in that way, we will keep tracking, or not on the whole. Maybe I can share my screen again, just a second. Very shortly. Can you see the screen again? So the registered models, the one that we register, are in this models folder over here. So yeah, if we want to keep track on the models, we could say DVC add ML runs models. Yeah, just there. Okay, and now this will create for us, for each file, it will create version 1. Yeah, actually, it's not creating. Maybe I need to reload again. Models.dvc. Yeah, it's actually hashing the whole folder. That's why it just created one DVC file. But yeah, when we do later git reset, we can restore to a previous version of the model.
So there are so many questions. Maybe we can take one final question. So how about using VS Code? Also, why do we use MLflow? Can another library help us? What is the benefit of MLflow? Is there any overfitting? The F1 score is very high. What other values do you pay attention to?
Okay. Yeah, I'm reading the question, so I'll cover. Absolutely, you can use VS Code as long as you have installed all the plugins that are necessary for Python and for Jupyter. Yeah, there are other libraries. There are Kubeflow. I don't have any concrete answer to compare them. It depends on the use case. It depends on what do you need to achieve. I think like MLflow is like the standard library of choice for everyone when starting with MLOps for beginners. Overfitting. I mean, this is a classical school book dataset, and it's expected to achieve high accuracy and high F1 score. So it's just a classical school book dataset. That's why it's in the scikit-learn library. It's for beginners when you play around with models. Of course, that shouldn't happen on real production data.
So maybe you can reply the other questions later.
Yeah.
Thank you for the implementation and thank you for your contribution. So
it was a pleasure.
So we will have a lunch break now. So after the break, we can continue with the next presentation, which is protein language models and using them for downstream prediction tests. So we will be back at 2:30 Turkey time and 1:30 European time. Thanks.